Okay, I would have said it is a pleasure to be here, but unfortunately I got COVID, as you may know, and I really hope that I didn't expose any of you. So my talk is on the Sachdev-Ye-Kitaev model, on which I spent most of my time during the past 6 years actually. And okay, I did something wrong with the preview, but that's fine. First, I want to show my collaborators. Some of them there was looking for a permanent job, also Tomoki, and Lucas got a postdoc in Cambridge, and Yiping a postdoc at the Chinese Academy of Science. There are many papers, and I want you to pay attention to this paper, which is from 1984. This was my first paper on the Sachdev-Ye-Kitaev model, probably more than 30 years before the model was invented. This is only for reference. So I start with an introduction connected to random matrix theory and topological insulators. Then, okay, so I forgot to update this. That's fine. Then I discuss chaos in the SYK model. I discuss coupled SYK models and dissipation in the SYK models. For topological insulators, you have typically a second quantized Hamiltonian, where the psi alpha and beta are fermionic operators, creation and annihilation operators, and H alpha beta as a lattice Hamiltonian with disorder. And the idea of topological insulators is that the bulk in d dimensions is disordered, where with localized wave functions, while the edge states are not localized. And the edge states are described by Goldstone bosons based on a coset G mod H that depends on the symmetries of the model. So we will have non-trivial bound states, non-degenerate bound states, if there's a non-trivial homotopy group from the edge to the coset. And also the topological insulators were first discovered in the context of chiral fermions by David Kaplan, and later in the context of condensed matter physics. There are issues with topological insulators. One issue is that we really have many body physics. The many body Hamiltonian may have different localization properties than a single particle Hamiltonian. Particle Hall excitations might still be the same universality class as a single particle Hamiltonian, but certainly not higher excitations. Also, interactions may change the universality class, as first was shown by Lucas. Fermi liquid theory is really the basis of topological insulators. We will be interested in non-Fermi liquids, where the concepts of a Fermi sphere and single particle excitations are invalid. Another thing is that nonlinear sigma model of the concept can only be realized if the macroscopic theory is chaotic or disordered, and that is one of the points I want to get across, and that the Low energy sector might not be a single sigma model. It might be a transition between two different sigma models, and we know examples of that as well. So topological insulators are classified according to random matrix theories. In total, we have 10 Hermitian random matrix theories. There are 3 Wigner Dyson ensembles, which are Hermitian matrix which can either be real complex or quaternion real. There are 3 of them. There are 3 parallel ensembles which have this block structure, like the QCD-Dirac operator, and that was the reason I introduced them. There are anti-symmetric and anti-self dual Hermitian matrix. So instead, these are full matrices introduced by Mehta and Rose's slide, and Mehta and Pandey. And finally, there are parallel ensembles where the off-diagonal block is complex symmetric or complex anti-symmetric. These were introduced by Alex Altland and Martin Sterenbauer, and these were the last 2 ensembles which were discovered, and that is why this classification is now called the Altland-Sterenbauer classification. And you can also represent all these ensembles in terms of Dirac operators in different dimensions. For example, this would correspond to 3 dimensions. For 2 dimensions, you have a number of other these ensembles depending on the boundary conditions you choose. Each of the random matrix theories can be expressed in terms of a nonlinear sigma model. These are, in QCD language, these are the flavors. And I give you only 2 examples for 2 different random matrix. These are the Hermitian random matrices, and these are the chiral random matrices corresponding to the Dirac operator in 4 dimensions. This would be the Dirac operator in 3 dimensions. In 4 dimensions, we have chiral symmetry. N would be the number of flavors, UN cross UN broken to UN. And for 3 dimensions, the chiral Lagrangian is based on the taking of U2N to UN mod UN. Then the homotopy group in this case is Z, the pi 2, and that is why we can add a Chern-Simons term to the Hamiltonian. And in the presence of the Chern-Simons term, we can actually have a different taking of I really shouldn't call it chiral symmetry of U2N to UN plus P times UN minus P, which was first discovered by Zoha, and we gave an explanation in terms of random matrix theory. For QCD in 4 dimensions, the pi 3 is a non-zero, and because of that, we can add a non-trivial Western term, which turns fermions into fermions. Again, disorder and chaos is important. The QCD, the disorder and chaos are due to the quantum fluctuations of the gauge fields. Also, this is known for a long time. These sigma models for parallel Lagrangians for QCD, I mentioned here Coker et al. Because they consider a wider variety. In the condensed matter literature, unfortunately, they usually cite Gade as the inventor of the chiral Lagrangian. When we look at, you can actually have a very rich phase diagram for QCD in 3 dimensions. This is just an aside, and because the potential has many minima, and from each you can jump from you have first order phase transitions from one minima to the next minima, and you really have a cascade of phase diagrams where the phase diagram in the temperature coupling plane is broken up by this remarkable line. But I won't discuss this any further. What are my goals? So we have seen that topological insulators can be classified according to random matrix theory. So we need disorder and chaos. So we want to study disorder and chaos. We also want to study non-Fermi liquid many-body systems. And the question is, when are many body systems fully quantum chaotic? And how does dissipation affect the possible phases of matter? Also, if you have questions, you can always interrupt me. You probably have to shout a little bit harder than usual. So I'll first start with now with the introduction of the SYK model. I actually have a little bit older version of my talk, which has not the right sections in here, but the rest is the same. So what's the Sachdev-Ye-Kitaev model? It is a model of Majorana fermions, chi alpha, chi beta, chi gamma, chi delta. Q is the number of fermions in interaction, and they are coupled via random couplings, Gaussian random couplings, which are real. The Majorana fermions satisfy these anti-commutation relations, which means they are just QCD gamma matrices in n dimensions. So if you have n Majorana fermions, they are gamma matrices in n dimensions, and that means that the dimension of this Hamiltonian is 2 to the power n over 2. The Majorana fermions you can decompose into complex fermions, writing them as the sum and difference of AK and AK dagger. And if you substitute that, you see that this Hamiltonian does not conserve particle number. And that is one of the reasons to consider it, because the Hamiltonian is less constrained, which makes the mathematics simple. So the Sachdev-Ye-Kitaev model actually first was invented in nuclear physics by French and Wang and Boigas and Flores and Mon and French. The model of Mon and French is this Hamiltonian, where you have fermionic creation and annihilation operators coupled by random matrix elements. We always called this model the two-body random ensemble, but now it is called the complex SYK model. The model is identical to the model of Mon and French. And the reason really why I started working on it is because Bruce French did his sabbatical at the University of Utrecht, where I was a student. And I never met him there, but he left a stack of papers in the office of my advisor. And my advisor asked me to look at those papers. And that is why I studied this model during my PhD. This model is very close to the nuclear two-body interaction. If you look at the matrix elements, they are kind of random. And that was really the motivation of French and these authors to introduce that model to understand the level, to better understand the level structure, the level correlations of nuclear physics. One important property of this model is that the level density of this model is given by the Bethe formula. That means it behaves like e to the power square root of energy. That was actually first discovered by Kitaev. It was never discovered in the nuclear community in the 70s and 80s. There have been many papers written on this model in terms of the nuclear literature, and here there are a couple of review articles. There are hundreds of papers actually have been written. The contribution of Sachdev and Ye is that they realized how to take the large N limit of this model. In the nuclear physics context, this was not really well understood. It was only understood in terms of a Gaussian limit of the spectral density. So the spectral density of this model is more or less a Gaussian, but it has a very long tail. I write down here some properties. So by studying this model, it is a model of compound nuclei. It is a model of many-body common chaos. It is a non-Fermi liquid. The zero temperature entropy is extensive. That means none of the statistical mechanics you learned in school is actually valid for fermions, because there are no particle hole excitations. The levels near the ground states are exponentially close in the volume or in the number of fermions. The model is chaotic, and that it saturates chaos bound obtained by Maldacena, Schenker, and Stanford, which tells that the Lyapunov exponent, that is that this is bounded by 2 times the inverse temperature, and this is the Lyapunov exponent of shock waves in black holes, and that is why the gravitation community got interested in this model. The model also has a reparameterization invariance, and based on that, you get the Schwarzschild action, and that is the low energy limit of 2-dimensional gravity, known as Teitelbaum gravity. So to classify the SYK model, it is based on the properties of gamma matrices. Gamma matrices have a charge conjugation symmetry and a chiral symmetry. So the charge conjugation operators are the product of the even or the odd. This should be a 1. Gamma matrices times the complex conjugation matrix, and the gamma 5, I call this gamma chiral, is the product of all gamma matrices. And these C's, the squares, are either plus or minus 1, and they either commute or anti-commute with the gamma C. And based on this, you have 8 different possibilities, and that gives the so-called Bott periodicity. That if you add 8 to the dimensions, the gamma matrices again have the same symmetry properties. For example, when the dimension is a multiple of 8, then the gamma matrices are always real, or can be taken real. Then in the SYK model, you have the product of 4 gamma matrices, and then not all possibilities are realized, only 3 are realized, and the reason is that the C1, the charge conjugation matrix, does not always commute with the chiral projector. That means the projector on a sector with either a positive gamma 5 eigenvalue or negative 1. And for example, when you have n equal to 2 in 2 dimensions, 2 fermions, then chi1 is sigma 1, chi2 is sigma 2, and gamma c is I times sigma 2, sigma 3, I sigma 2 times sigma 2, this is equal to sigma 3, and the projection on its eigenvalues is 1 plus or minus sigma 3, but this does not commute with the charge conjugation operator sigma 2 times complex conjugation. Okay, so next I want to address chaos in the SYK model, and there are different ways to measure chaos. One way is to do it by looking at the correlations of the spectra. This was first introduced by Boy-Bass, Giannoni, and Schmidt in 1984, who showed that if a system is chaotic, its eigenvalues are correlated according to random matrix theory. Another way, which has been used for the SYK model, is by measuring the out of time order correlator. This is the correlation functions of 4 fermions, where the time is out of time order. You have T0, T0. It is damped by this Boltzmann factor, and for t equal to 0, I have to divide by 1 over c. This is equal to 1 because you just have the product of 4 gamma matrices, but it deviates exponentially fast from this 1, and this lambda is the Lyapunov exponent for which Mavesena, Schenker, and Stanford invented this upper limit 2 pi beta, which is to this beta, and that is really proved in terms of properties of complex analytic functions. And the reason Kitaev got excited about the SYK model is that it saturates this upper limit in the low temperature limit. Previously, he had tried to find other models which saturate this limit, but that didn't work, other spin models. So there are a number of important time scales. One is the Lyapunov time, that is 1 over the Lyapunov exponent. There's the Ehrenfest time, which is log of n times divided by the Lyapunov exponent. It's also known as the sampling time. There's the Fowler's time, and that's a time scale beyond which eigenvalue correlations are given by random matrix theory. And finally, there's the Heisenberg time, which is a very long time, equal to the inverse level spacing. A nice introduction to the timescales was given by Outland and Sommer. So eigenvalue correlations can be measured by the pair correlation function. So this is a two-point correlation with the disconnected part subtracted. It has two contributions. One is self-correlations when the two eigenvalues, two arguments are equal. And in random matrix theory, you find a universal factor. This is given by the sine square of the difference of lambda and lambda prime times the level density times pi divided by the square. And this behavior is strongly universal. It has been found in many systems all over physics, like hydrogen in a strong magnetic field, in nuclei, in low-dimensional systems, in QCD. It is possibly the strongest universality we know in nature. To study the spectral statistics, we can look at a number of observables. The first one was considered by Wigner for the statistics of the levels of nuclei. This was the level spacing distribution. Another one is the number variance, which is the variance of the number of levels in an interval that contains n levels on average. But today I will discuss the spectral form factor, which is the Fourier transform of the pair correlation function. And it involves all eigenvalues, and to actually, it only becomes universal after you do a local rescaling of the average of the eigenvalue spacing, and that's called unfolding. So the spectral form factor is the Fourier transform of the pair correlation function, which is equal to the trace of e to the power IHT times e to the power minus IHT with the disconnected part subtracted. And in terms of you can express that also in terms of the pair correlation function. You can express in terms of eigenvalues and delta functions, where you have delta peaks at the point of each eigenvalue. For large T, only eigenvalues where E is very close to E prime survive, and that means only this term survives, and that means the Fourier transform of the pair correlation function has to become a constant for large T. For random matrix theory, it looks like as follows, and this is the spectral form factor. It goes up linearly for the GOE, complex emission matrices. Real symmetric matrices, it goes like this. And for ternary matrix, it goes like that. It is known analytically, and this is just a linear function up to this time scale, which is the Heisenberg time, which is normalized to 2 pi in this figure. In the SYK model, you can calculate the spectra numerically by looking at gamma matrices. In this case, for gamma matrices in 26 dimensions. And what is plotted here is the form factor versus time. Also rescaled to Heisenberg time equal to 2 pi. And the rescaling has been done by dividing the spacing of consecutive levels by the local average level spacing. And you see the analytical result is in red, and the numerical result is in blue. And you see the enormous accuracy in the agreement. There is no fitting in this figure. This is just what comes out of the box. One thing is there's this parameter here, which I did some filtering, and the filtering which I did is that the Hamiltonian is a four-body Hamiltonian, and that means that you have far fewer matrix elements in the Hamiltonian than you have in the defining Hamiltonian, two-body matrix elements. Then you have matrix elements in the many-body Hamiltonian. And because of that, you get what I call collective fluctuations, which I have filtered out.
Can I ask a question?
Yes.
So maybe, I have misunderstood the point, but you introduced some time scale beyond which so random matrix theory nicely reproduces the result. But according to this figure, over a whole range of time, they seem to completely match it. And how this is possible, or what is happening here?
If you look very carefully at zero, you see a tiny little deviation. It is extremely little. The deviation is very, very small. This is, you would have to plot it on a logarithmic scale, then you see better the deviations. But it is maybe on the order of, I don't know, 100ths or something like that. 0.01. Yeah. So the agreement is really unbelievably good. It is much better than I have ever seen in other models. For example, for the QCD Dirac operator, the agreement is not by far as good. One of the reasons is that you have very large matrices, exponentially large. You have 2 to the power n over 2, and this is how it works.
I see. Thank you. Thank you. Yeah.
You can also do a different thing because you might not like the unfolding by rescaling according to the average level spacing. You could do something different. You could not do it, and then you still can calculate this correlator. There's no cooking going on. You just calculate it, and that is on the next slide. Then you get this figure, and where the SYK model is are the black curve, and now it is compared to an analytic curve, and what I have done is I have folded in the analytical result for the spectral density of the SYK model to get a different analytic curve, which accounts for the average behavior of the level density. And also in this case, the agreement is excellent. In this case, I did not do any filtering. You see the fluctuations are larger. Here you see a small deviation, but probably not in the resolution you have. I can see it near zero. If I magnify. I don't know if you see the magnification. Here you see the magnification, but it is very small. Okay, so how this calculated is the analytic result is I use the universal spectral correlator, which is just a curve that saturates, a linear curve that saturates to a constant, and fold in the spectral density according to this equation. You can also expand that in powers of tau. They actually all but the level density is proportional to the dimensionality of the system, and that is why this is also a so-called topological extension. Here, I did not normalize the levels to level density to 1/2 pi. So this is actually the Heisenberg time for these type of matrices. How I'm doing with time?
Maybe 5 minutes or so.
5 minutes. Okay. So I don't think you will see very much of dissipation. So we have been looking at coupled SYK models, which is known as the Mada-Sena-Shi model, when you have strong constraints on the classification. It is the following model. You have left fermions and right fermions. For example, you can take the left fermions as all even gamma matrices and the right fermions as all odd gamma matrices. They are coupled with the same matrix elements, and there's an explicit coupling between the left and the right ones with the newest coupling constants. This model has the property that the ground state is a gap. It behaves like mu to the power 2/3, and it is almost a thermal field double state. That means it behaves like a maximally entangled state weighted by a Boltzmann factor, where this beta is an effective temperature. So this model is chaotic when mu is not too small or not too large. When it is too large, it is dominated by this term, which is completely integrable. For some choice of gamma matrices, it is actually diagonal for some representation, which we normally use. And for mu very small, this is dominated. And here you get just a superposition of different spectra. Because of this ground state, this has become a model of wormholes, and there's a phase transition as a function of temperature related to the gap of this model, which separates a wormhole phase from a two black hole phase. This is also the model which recently got some controversial coverage because of a paper in Nature, where this model had been put on a quantum computer, and these authors, Japeris et al., actually used a fast version of this model, where a large fraction, something like 90% of these matrix elements were put to 0. And we showed that this actually does not change the property of SYK models. So the model CNRC models has unitary symmetries. It commutes with gamma C. It also commutes with a swap operator, which interchange the left and right gamma fermions. You can see that there's, to understand the classification of this model, you choose a representation where the even gamma matrices are real, the odd gamma matrices purely imaginary, and you choose the even gamma matrix as L and the odd gamma matrices as R. And then the Hamiltonian, these are all real. These are purely imaginary gamma matrices. The coupling matrix elements are real. So this one is purely imaginary. There's an I here. So that means that everything is purely real. And that means that the Hamiltonian is purely real, and that it has only one complex conjugation symmetry, one anti-unitary symmetry, which is complex conjugation, and that is why the symmetry class is A1 or is UE. I think my time is up. Yes. Yeah, so I probably don't show dissipation, which is an SYK model for the Lindblad operator. And you can look at my slides if you are interested. That there's actually quite some work in recent months. One of our competitors is a group from Princeton of Shinshu Ryu, which has resulted okay. Let's skip all of this and conclude. So this it actually has a phase transition which we do not understand in the gap as a function of the coupling constant. It has a very strange behavior. It first behaves linear and then there's a transition. So let me conclude. So what we have seen is that the SYK model and coupled SYK models are classified according to random matrix theories with a great accuracy, in particular, if you filter out the fluctuation, the scale fluctuations. This is with regards to the Lindblad operator. I did not discuss that. Yeah, the coupled SYK model is chaotic. It is also chaotic, and it has an exact thermal field double count state that is separated by a gap from the rest of the spectrum. I think that is all.
Have any questions? Go ahead.
I'm just wondering how this random matrix model match to JT gravity.
How that is related to JT gravity?
That's right. Because this way,
Yeah. There are a number of steps involved. So the first step is that you write down a path integral for the SYK model as a in time only, a quantum mechanical you write down a quantum mechanical path integral in terms of fermions, which are now Grassmann variables as a function of time, with